Hello, everyone. We are now finished with Unit 3, our unit on energy and sound, and today we're going to be moving on to our fourth unit of the course, which is waves. Sorry, did I say energy and sound? I meant energy and society. I apologize. We're going to move on to our fourth unit of the course, which is waves and sound. Now, part of what we're going to do today is going to be a bit of a review from our first unit of the course. We're going to get through that pretty quickly and then move on to the new stuff. So here you basically have a group of little stick people doing the wave like you might do at a sports event. So what we're going to do is this, this is actually called the wave if you do it at a baseball game or something. And what's going on here is that what I want you to take away from this is that the people, who are sitting and then standing when it's their turn, they aren't actually moving from side to side. They're moving up and down. And yet, like if you look at their heads, for example, this is really clear. And yet there does seem to be some kind of wave, something moving from left to right. Okay, so although the individual people aren't moving left to right, nevertheless, there is something moving from left to right. Okay, so let's just start talking briefly about vibrations. Now, we've done this before in this course at the very beginning of the course when we worked with the ticker timers. And the ticker timer, if you'll remember, had the hammer which went right? It vibrated 60 times every second. So although I use the example of a pendulum here, our first example of periodic motion was the ticker timer. And in that case, the hammer came down 60 times in a second. So you could work out what the time was between one hammer strike and the next. So when we talked about that, there were two words and equations that were important to us, the words being frequency and period. And the frequency was how many times per second did the hammer strike happen, right? So in that case, it was 60 times per second, or 60 hertz is what we said. So that was the equation that we use in that case, right? So in that case, if we wanted to know what the frequency of our ticker timer was, we had to know that it struck 60 times in 1 second. So this would be 60, and this would be 1, right? 60 strikes or 60 cycles. 1 second, and then that would give us the frequency. Well, 60 divided by 1 is just 60, so that was easy. The slightly more difficult one is how long does one cycle take? In other words, from one strike, boom, to the next, boom. How long does that take? So how much time does that take in seconds? And so the equation looks similar, although it's actually the reciprocal. So in this case, we would say, okay, well, in 1 second, we have 60 strikes, 60 cycles. So 1 divided by 60 would give us the time, but from one cycle to the next. And there's a relationship because these are reciprocals. Then there's this reciprocal relationship that shows up as well. Okay, so moving on now to waves, right? Again, the graphic at the beginning. That's an example, that's an example of a mechanical wave where we're transferring that wave. What is it? Well, it's actually a transfer of energy from one person to the next if you're doing the wave at a baseball game. So this wave or this energy travels through a medium. So again, those people at the baseball game, those people are the medium. However, we're going to more generally talk about mediums being, our usual states of matter, solid, liquid, or a gas. So the liquid medium is probably the one that you're most familiar with. If you ever go to the beach, then you'd see those waves coming in to the shore. And so in that case, the medium would be the water, right? The liquid. So if you ever jump into a pool or jump into the lake or that sort of thing, you'll know there's a big splash, and that is a pulse. That's an example of a pulse or a shock wave, right? If you jump into a pool and you do a big cannonball, then there's a big explosion of water that creates a pulse or a shock wave, which ripples outward, radiates outward. So if you imagine that this is the surface of the water, if we do our cannonball there, then the big wave will go out away from us. Another way to imagine this would be if you had a rope, right, like a jump rope or something like that, or maybe a cable, you could whip one end of the rope and it would send a pulse down the rope. Okay, so this leads us to the two kinds of waves. The first kind is called a transverse wave, where particles vibrate at right angles or perpendicular to the direction of the travel of the wave. So that's kind of a still one, not very exciting. I'll get you a little GIF in just a second. The other kind is a longitudinal wave, which is when particles are vibrating along the direction of the travel. So something like that. Okay, so again, these still images aren't really super for looking at this, but just bear with me a second while I go through some of the vocabulary here. So when we have a wave, a transverse wave, actually, there are a couple things, a couple words that we use to describe the parts of the wave. Some of these words may be familiar to you from your grade 11 math class, but just in case, we're going to go through them all anyway. So the first thing is, so if we have our wave here, right, going up and down and up and down, we want to know like how long, we want to have a number for how long the wave is. So the length of the wave, also known as the wavelength, is the distance measured from one crest to the next, right? The crest being this part of the wave where it's the biggest, right? So from here to here, this is one crest, then the next crest, and then that distance, like it's an actual distance, right? You can measure it with a ruler. That's known as the wavelength. Similarly, the bottom part of the wave, the part where it's the lowest, is known as the trough, right? Trough. I know it doesn't look like it should be pronounced trough. Maybe it should be pronounced trough or something, but it's actually trough. Anyway, the bottom part is the trough. So from here, from this trough to the next trough, is also one wavelength. Okay, so that's basically how that works. The middle part of the wave, the part that cuts through the middle of the wave here, we call that the equilibrium position. Okay, in math class, I think you call that the axis, but in physics, we typically call that the equilibrium position. And then one word which is the same as in math class is the distance from the equilibrium to the crest, or alternatively from the equilibrium down to the trough. That's known as the amplitude. Okay, so definitely some vocabulary to know there. All right. Okay, so that's, now if we have a longitudinal wave, there's one word that we keep the same, and that's the wavelength, right? But there are a couple things that we do that are different, and this is because the wave looks different. So so you might wonder what kind of wave might look like this. Well, if you ever have played with a slinky, right, a long wire that's been coiled up, you can actually send a pulse down the slinky like this. Like if the slinky is into the camera like this, you would just do like this, and the slinky would, send the wave down like this and then back again. So the parts of the slinky where the coils are close together are known as the compressions, and the parts of the wave where the coils are far apart are known as the rarefactions. Rarefaction. I'm pretty sure it's rarefaction. I think there might be a typo there. There, this one's right. Rarefaction. There you go. There's a typo in the graphic. Anyway, so, and the wavelength is said to be from where you have one compression to the next, right? So there is still this idea of a wavelength, even though the longitudinal wave looks very different from a transverse wave. Here's a little gizmo where you can actually see the two different kinds of waves. So I'm going to start off with the transverse wave. So if I start this one going, you can see this is basically meant to be a slinky. Turn the lights off, actually. So this little dot is meant to be like a little LED or something attached to the slinky. So you can kind of see that this is meant to be one coil of the slinky. And so you can see that that little dot is moving up and down, right? It's moving up and down, clearly. But which way is the wave moving? Well, the wave is moving towards the right. Okay, like if you just kind of follow it along with your eye, it's moving to the right. So in this case, the particles or the coils of the slinky are moving perpendicular to the direction of the wave. Okay. So compare and contrast that with a longitudinal wave. So there's still that LED right there. And so in this case, if we run it, this is where you push and pull on the slinky. And if I turn the lights off, you can see that that little coil is moving left and right. It's moving left and right, just like the wave is moving to the right. Okay, although that's a little bit harder to see. It's a little bit hard to see the motion of the wave in a longitudinal wave, but if you just kind of follow the compression along, it's like it compresses along to the right. Anyway, take my word for it. Or not. Okay, so let's go back to the presentation here for a second. So we've talked a little bit about, I've tried to connect this idea of frequency and period, but those don't seem to really have much to do with a wave. I want to suggest that they do have something to do with a wave, because again, this idea of the ticker tape timer with the repeated motion of the bam, 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 although it doesn't look like a wave, it actually has some wave-like characteristics. Like if you think about the amplitude, if you were to measure what the hammer on the ticker tape were doing, it'd be going up and down, up and down, up and down. And so that's a kind of periodic motion that if we were to plot that versus time, we would actually see the hammer of the ticker timer going up and down and up and down. So it would actually be kind of like a sinusoid. So in this case, what we want to do is we want to somehow connect this idea of something that has a period or something that has a frequency to a wave. And yet, you know, the wave is moving. So we have to think about this really carefully. So the idea is like if these dots were representing, actually no, I'm not going to say that. So we want to add a little bit of math to this kind of motion here. Now this is going to look a little different from what you've seen in your math class, right? I'm not going to represent this as a sinusoidal function. That tends to come in a later physics course, not in this one. But nevertheless, I do want to attach some math to this one. And so the idea is, and this should hopefully work for whichever kind of wave we're going to talk about, whether it's the transverse wave, which looks like that, right? Or like in the gizmo I just did. Or, so in this case, again, the wave is moving to the right, I guess. It's a little hard to tell. But the particles themselves, again, this could be like water particles, right? And so the wave is moving through the water. The water particles are moving up and down, but the wave is moving left or right. And here's the longitudinal wave, where again, the wave is moving to the right, I guess. And yet the particles, if you look carefully at them, are actually vibrating a little bit left and right. You got to look closely there. So regardless of what kind of wave we're talking about, we want to come up with an equation which describes it. So we have this thing which is moving, right? We have this thing which this wave which is moving, and so therefore, since it's moving, it has to have a speed. So one of the very first equations that we talked about in this course is the idea that speed is a distance divided by a time. Okay, now here I've written it with the deltas, right? Because normally when we use this equation, we had a graph. But if you just remember back to the basics, speed equals distance over time, what kind of distance might we talk about with a wave? Well, I already said that if we measure from one crest to the next, that's one wavelength, okay? The length, right? It's right there in the word. Length is a kind of distance. So wavelength is what we're going to use for our distance in this case, right? And so wavelength is usually measured in meters. And the time, okay, we need a time. And again, this goes back to this idea of the periodic motion. The time that we're going to use is in fact the period, right? The time for one wave, the time for one cycle or one vibration is the period. So period has units of seconds, usually. So then if we put those two things together, we then have our wave, we get a wave equation. We get a speed equals distance divided by time. But if we use these two variables that I just talked about, we're going to use, instead of distance, we're going to use wavelength. Instead of time, we're going to use period. And so our equation becomes this one. Speed equals wavelength divided by period. Okay, that's it. Perfect. So if we know, for example, what the wavelength of our wave is, and we know the period, right? How long does it take to travel that distance? Then we're good. We know what the speed is. And so this actually works for any wave. It doesn't matter if it's a water wave. It doesn't matter if it's a slinky. It doesn't matter if it's a wave of people, at a baseball game. Any wave which will obey this equation. Now here's the thing. Period can sometimes be a little tricky to measure, right? If you're trying to measure how long does it take for one cycle to pass, that often can be very quick. I mean, think back to the ticker timer, right? I mean, if you're trying to measure the distance for one hammer strike, there were 60 of those in a second. It's really difficult to measure the time for one of those things. So instead, what we usually use is the frequency. And so if you remember that the frequency is the reciprocal of the period, or has this relationship, in other words, then our universal wave equation starts off as this, but replacing the period with with its reciprocal frequency, we get this equation, right? This is the universal wave equation. Speed equals frequency times wavelength, or V equals F lambda, if you prefer. Okay, if I didn't mention it, sorry, this is a Greek letter here. It kind of looks like an upside down Y, and the way that you say it is lambda. Okay, that's the way that you say that letter. Okay, so that's enough. Basically, I hope to get you started, and there's just a couple questions in the textbook that I'd like you to do for practice. Okay, thanks very much, folks. I'll see you next time.